Wayne Aiden McCoy, Riverside, California, 2019. Energy. The law of conservation of energy. We have now gone as far as we conveniently can in considering the intertwining strands of the atom and of electricity. It is time to turn to the third strand, energy. To physicists, the concept of work is that of exerting a force on a body and making it move through some distance. To lift a weight against the pull of gravity is work. To drive a nail into wood against the friction of its fibers is work. Anything capable of performing work is said to possess energy, from Greek words meaning work within. There are various forms of energy. Any moving mass possesses energy by virtue of its motion. That is, a moving hammer will drive a nail into wood, while the same hammer held motionlessly against the nailhead will not do so. Heat is a form of energy, since it will expand steam that will force wheels into motion that can then do work. Electricity, magnetism, sound, and light can be made to perform work and are forms of energy. The forms of energy are so many and so various that scientists were eager to find some rule that covered them all and would therefore serve as a unifying bond. It did not seem impossible that such a rule might exist, since one had been found in connection with matter that appeared in even greater variety than energy did. All matter, whatever its form and shape, possessed mass, and in the 1770s, the French chemist Antoine Laurent Lavoisier, 1743 to 1794, discovered that the quantity of mass was constant if a system of matter were isolated and made to undergo complicated chemical reactions. Everything about it might change, but not its mass. A solid might turn into a gas. A single substance might change into 2 or 3 different substances, but whatever happened, the total mass at the end was exactly the same, as nearly as chemists could tell, as at the beginning. None was either created or destroyed. However, the nature of the matter might change. This was called the law of conservation of mass. Naturally, it would occur to scientists to wonder if a similar law might hold for energy. The answer wasn't easy to get. It wasn't as simple to measure the quantity of energy as it was to measure the quantity of mass. Nor was it as simple to pen up a quantity of energy and keep it from escaping, or from gaining additional quantity from outside, as it was in the case of mass. Beginning in 1840, however, the English physicist James Prescott Joule, 1818 to 1889, began a series of experiments in which he made use of every form of energy he could think of. In each case, he turned it into heat and allowed the heat to raise the temperature of a given quantity of water. He used the rise in temperature as a measure of the energy. By 1847, he was convinced that any form of energy could be turned into fixed and predictable amounts of heat.